Welcome to qnawire.
Once again, welcome to a new problem involving a spring. There's a pole with a spring hanging on it, and the spring is not stretched. The spring constant K happens to be 76 newtons a meter, and it's a vertical post. This is the ground level, and so there is a block hanging on the spring, and the mass of the block happens to be 2.00 kilograms. So the spring is neither stretched nor compressed, and that's going to be helpful to the problem. So the string is neither stretched nor compressed. There's going to be a force, a constant horizontal force of 54 newtons. Assume that it's going to push the spring this way towards that direction, and so as the spring goes up, it's going to be forced to stretch. So it's going to stretch a little bit. Okay, the spring starts to stretch as it's pushed in the right direction. The block is still there, and this is an energy problem. So part A of the problem, we want to find out what's the speed of the block when the spring is stretched 4 meters. So this spring right here, we're going to say now it's being stretched x equals to 0.400 meters. That's the scenario we have for the block, and we want to find the velocity. We want to find the what's the speed of the block when it's being stretched that way. So we want to find this velocity. The block is moving towards the right. Okay, what's that velocity? Using the work energy theorem, we get to see that the total work done. So the spring, total work done by the spring and the force equals to change in kinetic energy. And so we have work done by the force, and then we also have work done by the spring, and the change in kinetic energy is 1/2 mv final squared minus 1/2 mv initial squared. The goal is to find this final velocity. We know the initial velocity is 0 meters per second, and so using this formula, we're going to plug in. We're going to go up here and say the work done by the force is the force itself times the displacement. The spring is opposing that movement. So it's resisting, and so we're going to have a negative right there, 1/2 kx squared equals to 1/2 mv final squared. Remember, this whole initial kinetic energy is 0 because the initial velocity is 0. It's always a good habit, like we said before, to solve for the v final, and we're going to do that in the next page. So we have fx minus 1/2 kx squared equals to 1/2 mv final squared. This is our target, the final velocity. So multiply everything by 2 to make your life easier. We have 2 f times x minus kx squared equals to mv final squared. Divide everything by m. And so mv final squared equals to 2f times x minus kx squared all over m. So if we want to get the final velocity, we need to get the square root of that. So the square root of 2, 2 times the force times the displacement minus k x squared over m. Next thing is to plug in the numbers related to that. So we have v final equals to 2. If you go back, you see that the force happens to be given as 54 newtons. So F equals to 54 newtons. That's the force that's pushing it. So this is times 54 newtons times the displacement 0.04 meters minus K. If you go back, you see that K happens to be 76 newtons per meter. 76 newton per meter times x squared, which is 0.04 meters squared. And then we don't forget to divide by the mass itself. And the mass happens to be, if you go back, the mass is 2 kilograms. So 2.00 kilograms. Just make sure this radical goes all the way. So the final velocity happens to be, if you plug in those numbers, I'm going to use my calculator. So this is square root of 2 times, actually I need 2 brackets. So square root of 2 times 54 times 0.04 minus 76 times 0.04 and another 0.04. We need a bracket there. So this one right here, there's a bracket here, so don't forget that. So 76 times 0.04 times 0.04, close the bracket, the second bracket, divide by 2 and close the bracket, and that gives us so we need to do that problem again, 0.320. If we plug in the numbers, we'll see this is square root of 2 times 54 times 0.04, close that, minus 76. Well, actually, it's not 0.04. It's going back to this, the x displacement happens to be, we need to find that. The x displacement is 0.4, not 0.04. So we have to rectify that. This one is 0.4, and this one is also 0.4. And so if you plug in the numbers, you get the square root of 2 times 54 times 0.4, close that, minus 76 times 0.4 times 0.4, close that, and that, divide by 2, and that's going to give us 3.939. So 3.939, which is approximately a velocity of 3.94 meters per second. So once again, we wanted to find the velocity. We used the work energy theorem. If you go back, there are two components of the work involved. So the force that's pushing this way in the positive direction, that does work. This is the force, and also the spring is resisting that push, and that's why we have a negative right there. Remember, the initial kinetic energy is 0, so that's going to cancel out. We have Fx. Remember, if the force is constant, work is given by the constant force times the displacement. That's the left side of the equation. We move on and solve for V final. Always keep the variables up until the end and then plug in the numbers and you get the result. Part B of the problem says that, at what instance at the magnitude and direction, what are the magnitude and direction of the acceleration. So we're looking for the acceleration. We have a post. The post has initially has a spring hanging on the block, and then it's stretched and pushed that way because of a force F. The spring constant happens to be K, which, if you go back, it's given us 76 Newton per meter. So there's a force pushing to the right in the positive direction, but then the spring is opposing that movement with its own force. So the spring force is a spring force that's opposing the stretching. Using Newton's second law, we know that the net force, or the sum of the forces acting on the system, is mass times acceleration. We have the positive force and also the spring force, which is opposing. This side is positive, this side is negative. This is the spring, equals to ma. We want to find the acceleration. So acceleration is the force that's pushing in the positive direction minus the force of the spring, divided by the mass. The force that's pushing happens to be 54 newtons. The force of the spring is kx, over the mass is 2.00 kilograms. We plug in the numbers, we get to see 54 newtons minus k is 76 newton per meter. The distance of displacement is 0.4 meters over 2 kilograms, and that's going to give us a positive acceleration, which happens to be approximately 11.8 meters per second squared. So this is positive, which means that it's moving away from the post in this direction, so the right direction. That's the positive side. Thanks for watching the video. I hope you enjoyed it. Feel free to send me questions, and looking forward to helping you with more problems. So check out the videos and have a wonderful day. Okay, bye.